All right, so 8.4 has a title that makes it sound a lot like 8.3. 8.3's title was trigonometric as well, but this one says trigonometric substitution. And so you might be led to think, well, it must have something to do kind of like U substitution, and you would be kind of right. There is a substitution involved, and that's the substitution that we've seen most frequently. So the thing is, though, that these problems typically do not start out looking like anything that trig would relate to. These problems are going to look like radicals. And they're going to have one of these three forms. They'll either say the square root of a squared minus u squared plus u squared, or flipped around, it's u squared minus a squared. So these are the three forms these can take on. These are all related to the Pythagorean identities. So I will write down the first one as a reminder. Sine squared of theta plus the cosine squared of theta is equal to 1 is one of the three Pythagorean identities. Can you give me another one? Very good. Tangent squared of theta plus 1 is secant squared of theta. Yes. So these are the three Pythagorean identities. And we will be looking at them and using them as we're working through this. We're also going to be using the Pythagorean theorem, and we're going to be using it as well in a way, not necessarily that, but using triangles as well in a way that you would have seen in trig when you think of a SOHCAHTOA. So you nod your head if you know what I mean when I say SOHCAHTOA. Okay, good deal. We're going to be, we got a little bit like this going on. We'll make sure you got it, Caleb. Okay, so we're going to be using trig in this section, and it's probably been a hot minute since you took trig. How long's it been? Think. A couple of semesters? 3 years. Okay, so your trig might be a little bit rusty, and that's okay, but we're going to be using just a little bit of it, not a whole lot, okay? So the first thing I'd like to do, the first three problems on here, are me trying to show you where these trigonometric substitutions are coming from and why they work. Not because I'm going to ask you to show me where they come from and why they work later. That's not the point. The point is that they didn't just come out of nowhere, and it wasn't some super fancy mathematician that created them and is giving them to you and just telling you to take it at face value. There's a reason that these work, and I want to make sure you understand the why behind it before we start actually using it, okay? All right, so the first one that we're going to take a look at is trig substitutions. The three are actually for these three forms. These three forms have three different trig substitutions, and I want to establish where they're coming from. So we're going to go just in order. The first one is the a squared minus u squared one that we're going to look at. And I'm going to show it to you not just in one way, but in two ways, okay? So we've had discussions in our house recently about, do you like algebra or do you like geometry better? Okay, so one of these is a very algebraic kind of approach and perspective, and one of them is sort of like formulas and algebra, manipulation. And the other one's a very geometric style approach. I have 3 kids in my house right now, none of them like geometry, and they're all in it. Okay, so we've done a lot of geometry lately. So my kids were asking me the other day, do you like algebra or geometry better? And I was like, actually I do like them both, but when I was their age, I liked algebra a whole lot better, okay? I think you'll like geometry better on this one, but we'll just see, okay? So I'm going to show you the two ways to think about these. Okay, so the thing that you do need to be able to do when you're looking at these is to know this piece of information and or be able to use it. Now, I'm not showing you in this problem how to use it, but this is the substitution that you will make for u whenever you see square root of a squared minus u squared. This is the substitution. A is going to become a sine theta. I didn't say that right. U is going to be able to become a sine theta. And I want to show you how that simplifies the radical if we allow that substitution to take place. And we're going to do this is analytically or algebraically, by actually putting that u in as a sine theta and seeing what happens when we clean it up. So we're going to put in a sine theta in here for u, and it looks like this. Everybody good with that step? It's just substituting it in, and we're going to clean it up, okay? So we're going to clean it up now, so we're going to square things. So this is a squared minus And this is a squared then, and then sine squared of theta. Good so far? Okay. Now notice, well here, let me just say this. I'm going to say this because somebody's going to do it. You cannot take the square root of each piece. Okay, that is not okay. Some of you keep trying to. Some of my Calc 3 students keep trying to as well. Everybody would love that to be a property, it's just not. Now, what you can do is you can say, okay, I at least see that there's an a squared in both pieces. Do you see that? So in here and in here, they both have an a squared. So what I'm going to do is I'm going to factor a squared out in front. Now, if I factor a squared out of a squared, what am I left with? 1 minus what? Sine squared. Fantastic. Okay, now there is a property for radicals that says I can separate these two pieces apart because of the multiplication. So it doesn't work for addition and subtraction, but it does work for multiplication. So what's the square root of a squared? A. That's fine. Okay, we're good with that. Now, I still can't take the square root of 1 and the square root of sine squared. That's not going to work.
That's going to be cosine squared?
It is going to be cosine squared. So we're coming back to these Pythagorean identities, right? Sine squared plus cosine squared is equal to 1. So if I have 1 minus sine squared, which is what I have right here, I can replace that with cosine squared, which is just cosine. So what this is telling you, after having done all of this, is that this radical expression, if I make that substitution, has the form a cosine theta. Why does it matter? Well, because you already know how to take derivatives and antiderivatives of sines and cosines, right? We just did it in 8.3, even ones with powers on them. So we've changed a radical form something that can't be dealt with directly into a trig something that we can deal with. This is the analytical or algebraic perspective. Okay, you ready for perspective number 2? Okay, now I'm going to give you a geometry perspective. So I mentioned earlier SOHCAHTOA. So what does SOHCAHTOA mean? Okay, so the first one is sine. The S is for sine. Sine is opposite over hypotenuse, right? What about the K? Cosine, adjacent over hypotenuse, and TOA? Tangent is opposite over adjacent. Excellent. And while it doesn't have secant, cosecant, and cotangent, how could we find them with this idea? Reciprocals. Okay, everybody good so far? Like that's as much trig as we need to remember, really. Okay. All right, so we're going to draw a right triangle. And we're going to identify an angle theta in it. And we're going to take this substitution that we're making right here, and I'd like to rewrite it so that it's solved for sine of theta. So if I rewrite this, what is sine of theta for this equation? U divided by A. Everybody good? Okay, so in my triangle then, I've got the theta identified. Where will U go? Opposite, over here. And where will A go? Along the hypotenuse. Okay, how are we doing? We're good. I need an expression for the third side, but I don't want to just throw in more variables. I want the third side to be in terms of U's and A's.
A squared minus U squared is square root of A squared minus U squared is the Pythagorean identity for the Pythagorean theory for your hypotenuse, correct?
Okay, so it's going to involve the Pythagorean theorem. You're exactly right, David. Let's give this, I'm just going to call it question mark. You can call it the letter name if you want to. But the question mark being squared plus the U being squared is going to equal A being squared. True? Okay. So I could move the U squared to the other side. And then I'd need to square root. So this third side, this unknown piece down here, is the square root of a squared minus u squared. Does that look familiar? You see it on the screen? Yeah, it's right over there, right? That's exactly the radical that we're sort of looking to get rid of, if you will, right? To find another expression for. Okay, so now it's in the triangle, like it's one of the sides. That's helpful. And now I'd like to actually take a look at how I would manipulate, not manipulate exactly, but use this information in the triangle. I'm going to delete this. Use this information in this triangle then to have a relationship between the side that I want to have another expression for and the piece that's a constant. A is a constant. I don't know what it is, but it's a number, right? In any given problem we're going to be working with, it's going to actually have a numerical value. It's not going to say A. It's going to say 9 or 4 or 2/3 or something like that, okay? Okay, yeah, so this is the expression for those two sides. It's adjacent over hypotenuse, looks just like this. And you're right, I would like to move my a to the other side. So this is a cosine of theta is equal to square root of a squared minus u squared. And check it out. We're right back where we had in the other problem. So we can justify it from an analytical, algebraic approach or from a graphical approach. And this is number 1, right? A squared minus u squared, radical. We're going to do the same thing for the second one, a squared plus u squared. You're going to feel like we just did the same thing, okay? We're going to end up with a slightly different result. That addition will make things a little bit different, okay? And we're going to justify it in both ways again. So we are going to do it analytical first. So this is a squared plus. This u substitution, this trig substitution using the u is going to let u be a tangent of theta. So it looks like that. So then, this is a squared plus a squared tangent squared of theta. And what will we do? Factor our a squared out, which leaves me with 1 plus tangent squared. I can split it. This is the square root of a squared and the square root of 1 plus tangent squared. Square root of a squared is a. What is 1 plus tangent squared? Secant squared. And what is the square root of secant squared? Secant of theta. So this is a secant of theta. Right? So I can replace the square root of a squared plus u squared with a secant theta if I replace the u with a tangent of theta. I can make a replacement that changes it all around and I turn into a trig problem when it was originally a radical problem. Now let's take a look at the graphical approach. Same thing set up as last time. We're going to draw our right triangle, put in our angle theta, and we're going to take this expression and we're going to solve it for tangent. Tangent of theta is what? What is it?
Opposite over adjacent.
It is opposite over adjacent. In our equation, what is it?
It's
U over A. Okay, so it's U over A. And then the opposite would still be looking like this. Adjacent is actually going to be A this time, so A down there. What will the third side of my triangle be? It's easier to see this third one here than the last one. Yeah, it's the square root of a squared plus u squared, right? It's Pythagorean theorem in play. That's the same a squared plus u squared underneath the radical that I started with, or you could write it u squared plus a squared. It doesn't matter because addition is commutative. Alrighty then, and so what would I do to get a relationship then between this quantity that's in squared or in a square root form and the constant? So this is my 1 and this is my constant, right? So what's the relationship between these two sides of the triangle? Don't overthink this. What's the relationship between these two sides of the triangle? It's cosine, right? Adjacent and hypotenuse. This is cosine. So this is the cosine, whoops. Cosine of theta is adjacent, which is a, over the hypotenuse, which is square root of a squared plus u squared. Now, there's a couple of different ways that we can deal with this. We know we're supposed to be getting a secant theta at the end, but we know it because we already did this analytical approach, right? Like, we know that. But what we want is we really want to solve for the radical part. Agreed? The goal in both of these cases is let's figure out what the radical would be replaced with if I were doing this substitution. So if I solve this, I'm going to actually just multiply by the square root of a squared plus u squared. So this is square root of a squared plus u squared to the other side. And I'm going to divide by the cosine. Whoa. Okay, is that okay? It's kind of like cross multiplying and then dividing in the same step. But a over cosine of theta is the same thing as what? It's secant. Yeah, cosine in the denominator, the reciprocal identity for that is that it's secant theta. So we end up with a secant theta just like we expected that we would end up with from the analytical approach. Okay, there's one thing that I want to make mention, not because it affects us specifically in these particular problems when we're working, but because it's going to show you why something happens a little bit weird in a minute, is that these actually only work on certain angles of theta. And if you'll remember from like maybe a trig course somewhere, this happens because in trig, you can't do things without being one-to-one in certain perspectives. And so you have to sort of isolate that you're only looking at like quadrants 1 and 2 or only quadrants 1 and 4 in order to do inverse sines and inverse cosines and so forth. So it's coming about from that perspective. So on this one, this is the first one, number 1. It only works when you're in quadrants 4 and 1. So it's from negative pi over 2 to pi over 2. And the same is actually true for number 2. This only works in quadrants 1 and 4. So negative pi over 2 to pi over 2. Okay, so I'm mentioning it now because I'm about to make something happen that looks a little bit weird on our third one. So our third one that we're going to take a look at is the subtraction, but in the opposite order. Now I have the square root of u squared minus a squared. Says my substitution should be a secant theta, so we're going to do it analytically and we're going to make that happen. So my u is going to be replaced with a secant of theta squared minus a squared. Seems like it's doing the same thing. This is a squared secant squared of theta minus a squared. We factor out an a squared secant squared of theta minus 1. Okay, everybody good so far? All right, we can do the square root of a squared, and we can do the square root of secant squared of theta minus 1. What's the square root of a squared? It's a. What's the square root of what's secant squared of theta minus 1? That is tangent of theta. And squared, sorry. And what's the square root of tangent squared? Yeah, so this is kind of a tricky thing. It's not just tangent. It's actually the positive or the negative tangent of theta. And this is the only one this happens for, and it will be very obvious when you need to use the negative. But what ends up happening here is that you either end up getting a positive or a negative of a tangent theta. Try not to worry about the fact that there's a possibility of which one it is here, because it will solve itself very quickly. The angle here is actually between 0 and pi over 2, and then between pi over 2 and pi. So I'm able to be, good grief. I'm able to be, instead of in quadrants 1 and 4, I'm in quadrants 1 and 2. In quadrant 1, tangent is positive. In quadrant 2, tangent is negative. That doesn't happen over here. In quadrants 1 and 4, secant is positive in both of them. And over here, in quadrants 1 and 4, cosine is positive in both of them. So it's because of the quadrants that I'm forced into, because of the way this is happening with things being 1-to-1, that this is happening. So I mentioned that it's going to take care of itself, and it is going to take care of itself because it depends on which quadrant you're in as to the way you draw your triangle. Okay? So let's take a look at this particular one from a graphical approach, and then we'll stop here for today. So from a graphical approach, here's my triangle. Here's my angle theta, and here's my right angle. Let's take this equation and let's solve it for secant of theta. So what is secant of theta? U over A. Now, secant is not a sine, cosine, or tangent, right? But what would I do? Where would I put my U? Where would I put my A? So U will go where? So U will be on the bottom, and A will be where? Okay, so I think by side you mean hypotenuse. Will that work? Okay. Yeah, so it should be hypotenuse over adjacent. So instead of having it as adjacent over hypotenuse, which would be, did I write it backwards? Sorry, just a second. Oh, I'm looking at something else. No, we did. I still wrote it backwards. I was trying to be so careful, and I still wrote it backwards. Instead of being adjacent over hypotenuse, adjacent would be that the U was being adjacent to it. It will be hypotenuse, so U is going here over adjacent, which is A here. We'll get it right. Sorry. Between you and I, Joshua, we were just flipping it all around. Okay, U and A. What in the world is this third side? It is U squared minus A squared, and not only because that's what we're looking for, but because it really is, right? Really is. And then what trig function would I use to relate the two sides of the triangle that don't both involve U? So I've got U as my square root. The square root involves the U, and I've got the constant side. What will relate these two together? This is tangent. Tangent of theta is the square root piece. So U squared minus A squared over A. And if we replace it, over here A is tangent of theta is the square root of U squared minus A squared. So why did I get a positive instead of a negative? Because I drew it in quadrant 1. If this picture were drawn, let me draw it small underneath, but if this picture were drawn in quadrant 2, this piece right here would be negative. Let me draw in the axes to sort of show you what I mean. Right? That piece on the bottom, that A value would be a negative number, right? Because I would be over in quadrant 2. Same would be true if I was in quadrant 3. I'm just not. But over on that side of the graph, I'm at a negative A value. So this actually ends up giving me a plus or a minus, depending on the perspective in which I drew my triangle. That doesn't happen over here. Because if I draw this triangle in quadrants, okay, I don't have enough space. If I draw this triangle in quadrant, okay, I can't get it to it again. My goodness. There. I draw this triangle down here like this in quadrant 4, which would be the other option. And I could draw it that way. I still end up with an A value that's positive. Right? I understand the U is negative, but U is my variable anyway. That's not the quantity that I keep comparing things with. It's the A that I compare things with. So that's why that doesn't happen over here. Okay, so here's what's going to happen. We will finish this lesson next time, and the things that are left in this lesson is actually how do we use this information now? How do we go about taking these substitutions and doing something with them that makes it helpful to us? So I will table that discussion until next time, and I'll see you guys then.